Looking at the differential equation, since the point x equals 0 is not a singular point, we can try substitutions for y and the second derivative of y centered around x equals 0. We start by making these substitutions for y and the second derivative of y into our differential equation. Next, we distribute the power series on the coefficient 1 plus x squared. From here, we can simplify and include our x squared in the power series by increasing the exponent of x raised to the n by 2. Following this, we use a change of variables in our middle power series, which raises the start index by 2 and makes all exponents of x across the series to be n. Finally, we pull out all terms from series when the index equals 0 and when the index is equal to 1. This allows us to fully simplify the equation as a single power series. From this form, we can equate coefficients of powers of x and identify a relationship between a sub 0 and a sub 2, in addition to a relationship between a sub 1 and a sub 3, and finally, we can get a recurrence relation between every other coefficient of a when n is greater than 3. Looking back at the original differential equation, we can put it in standard form and notice a singularity at x equals plus or minus I. If we look at these points in the complex plane, we see that both points are a distance of 1 from the origin. As such, the radius of convergence for the power series solution will be 1. In part 2, we are given some information about the phase portrait for a differential equation, which relates dx dt to x by a matrix A, which has the complex eigenvalues 1 plus or minus 3i. Crucially, we note that the real part of each eigenvalue is positive. In addition, it is given that the rate of change of x along the positive y-axis is negative. This information, together with the positive real part of the eigenvalue, suggests that the phase portrait will spiral away from the unstable origin in a counterclockwise fashion.